All right, good morning again, ladies and gentlemen. Today, well, this is the second video of the day, and we're going to be going over question 2 of mock exam 3. If you hear a noise in the background, there is construction going on in my building, so please try to ignore it. I apologize ahead of time, but the show must go on. So anyway, this video, of course, brought to you by Couch Potato brand snack, foods, and beverages. So, question 2, again, of this very scary, very complicated mock exam 3. Once again, I want to reiterate that this question has way more parts than what you should expect on the AP exam. That being said, it's definitely good practice. Great practice. So let's get into it. I'm your host, Giratina. So we have the company, some company sells poke bowls. I hope I'm pronouncing that correctly. Poke? Not Pocky, poke. Is a bowl filled with various sushi-like ingredients to make a type of salad called a poke bowl. I actually had one of these last summer and they were quite good. So anyway, when customers order, they select between a bunch of choices, blah, blah, blah. Some ingredients are classified as premium and cost extra. And customers either choose between 0, 1, 2, 3, and 4. Okay? And so, well, the question says that they choose as many as they would like, but as it goes on, when they track the customer's purchases, the only values that apparently occurred were 0 premium, 1 premium, 2, 3, or 4 premium ingredients. So anyway, they give you this probability distribution. And I just want to point out that it's been a while since we've seen probability distributions, but remember, there's another way we can look at them. This probability distribution is equivalent to something like this over here, this kind of histogram, right? If we call our random variable x and we define x to be the number of premium ingredients chosen by a customer, well, then the distribution of x can be drawn to look like this histogram over here. All right, so just keep in mind that these probability tables are just simply distributions in disguise in basically, I guess, less visually appealing tables, but they are distributions nonetheless. Part A asks, what is the probability that a randomly selected customer selects 2 or more premium ingredients? Okay, pretty straightforward, but I'll go over it. Let's see. And so we're looking for the probability that x is greater than or equal to 2. And so, of course, I thought I selected highlighter, but maybe not. Yeah, there we go. And so, of course, we're looking to add up the areas of the bars above 2, 3, and 4, and the areas are exactly equal to the probabilities. So this probability is going to be 0.14 plus 0.08 plus 0.03. All right, and that's that. Oops. There we go. Let me get rid of the highlighter without getting rid of, there we go. All right. Part A is straightforward. Part B, if a randomly selected customer does select at least 1 premium ingredient, what are the chances that he selects 3 or more? So now this one gets a little bit more complicated because we are given some information, and given that information, we want to calculate another probability. So symbolically, using the P notation that I stress oh so much, this is equivalent to saying the probability that x is greater than or equal to 3, given that x is greater than or equal to 1. Of course, this is equivalent to the probability that x is greater than or equal to 3 and x is greater than or equal to 1 over the probability that x is greater than or equal to 1. Okay, right? And that of course is the relationship that says the probability of A given B is equal to the probability of A and B divided by the probability of B. I can't stress enough how important this relationship is. You definitely need to know how conditional, joint, and marginal probabilities are related to one another. All right, so now let's get to the situation at hand. That numerator, pretty straightforward. So I'm including all values except for 0. So the probability that x is greater than or equal to 1 will be 1 minus 0.42, which of course is 0.58. And sorry, that's the denominator. I said numerator, but I meant denominator. The numerator now is a little bit trickier. So you might remember that this symbol here, we use the word and in the context of probability, but you also might remember it as intersection. Okay, so we want to basically figure out the probability of the intersection of these two events. So x greater than or equal to 1 corresponds to this bar, this bar, this bar, and this bar. However, x greater than or equal to 3 corresponds to this bar and this bar only. And so what bars has both colored highlighters? Well, only 3 and 4. So the probability that x is greater than or equal to 1 and x is greater than or equal to 3 actually boils down to simply to be equal to the probability that x is greater than or equal to 3, right? Because again, these are the only two bars. Oops, let me get the regular pen. These are the only two bars that contain both the yellow highlighter and the orange highlighter, meaning those are the only two bars that where these two events intersect. And so that would be 0.08 plus 0.03, which is 0.11. So this will be your probability for part B. 0.11 over 0.58. Okay, let's get into part C where we start talking about the distribution. So what is the shape of this particular distribution? So shape, that means they want you to talk about skewness and modality. If you look at the table, you'll see that when the number of ingredients is low, the probability is high. And when the number of ingredients increases, that probability decreases. So maybe you didn't make the connection, but what that tells us is that we actually have a skewed right distribution with one which is unimodal. So there's a peak all the way at the left. To help you out, again, take a look at this histogram. You can clearly see that we have a unimodal distribution which is skewed right. Okay. I would, of course, phrase your answer in the context of the question. So you'd say something along the lines of the distribution of number of premium ingredients ordered by customers is unimodal and skewed right. Notice I didn't talk about center and spread or unusual features because they just simply told me to talk about the shape. They also go on and give you the mean and the standard deviation of this distribution. Just to be clear, we can actually calculate those values on our own. Couple of ways. You could either maybe input this information into list 1 and list 2 and calculate one variable stats with list 2 as your frequency table. Or for expected value, we can find the sum. All right, hold on, I'll be right back. All right, welcome back. So for expected value, remember we can take each possible outcome and multiply it by its probability and then sum all of those values together. In other words, we can get our expected value by taking the sum of each individual x multiplied by the probability of that individual x. And again, summing all of those terms together. In other words, like 0 times 0.42 plus 1 times 0.33 plus 2 times 0.14, so on and so forth. And you'll see that in this particular case, you do indeed get a mean of 0.97. Similarly, for standard deviation, there's a formula that says we could take the square root of the sum of x minus mu squared times the probability of each individual x. All right. I wouldn't say that the standard deviation formula is something you'll need to worry about, but I would say that you should know how to calculate the expected value given a probability model like this. All right. So anyway, they give us that information. Now part D. So 16 customers are chosen at random. That's a good word. When we're choosing a sample from a population, it's always good to hear that they're chosen at random. And they're chosen on a certain Saturday night. Describe the shape of the sampling distribution of the sample mean number of premium ingredients. So notice that now what we're doing is we're taking these 16 customers and we're finding their average number of premium ingredients ordered. And so if we were to, let's say, do this over and over and over again, we would get what's called the sampling distribution of sample means. All right, where did I put part D? Okay, so we're interested in X bar, the average number of premium ingredients ordered by a sample of 16 people. Let me get the word people in there. And the question is, well, what does this sampling distribution look like? Well, since we're talking about sample means, we want to know, does the central limit theorem apply? Well, there are a few aspects to the central limit theorem. As far as center, we want a random sample. The random sample will ensure that we have an unbiased estimator for the center of that distribution, specifically the mean. If we have a random sample, then our X bars will be centered at the population, the parent population's mean, which is 0.97. Okay. And we are given that information. But actually, reading it a little bit more carefully, it does say that we're only interested in the shape. So it's nice that we have a random sample that would guarantee us that the center of our sampling distribution would be equal to 0.97 over repeated sampling. However, that's not what the question is asking. The question is asking about the shape. And so what deals with the shape is what's called the nearly normal condition, or in other words, do we have a large enough sample size? So 16 customers is not quite at that magic number of 30. So we have to do a little bit more investigation. Now, remember, another way, when your sample size is not greater than 30, the other way to check the nearly normal condition is to look at the individual sample itself. So we just look at these 16 people and see, how the number of premium ingredients in that sample is distributed. And if that sample is nearly normal, then we're okay with saying that the nearly normal condition is satisfied. However, we're not given that information either, but we are told that the parent population is skewed right. So I want to show you a little bit. I want to show you a little something. Okay, those of you that are in my class definitely recognize, or I don't want to say the word definitely, but you should recognize this little applet here, which is a nice way of sort of seeing what happens with sample means when you have different sort of parent populations and different sample sizes. The way to get this applet, actually, just go to Google and type in sampling distribution applet, and you'll get there. Okay. So anyway, notice that our parent population is skewed right. This matches the parent population that we're working with here, okay? And they just so happen to have a sample size 16 option. They don't have too many options, but one of them is 16. So we're kind of lucky. Now look what happens. So here's let's say one sample that we've chosen. Okay, so that's one sample of 16. So this middle distribution here is the single sample. And that blue box that you see, that's the average of this sample. So that ultimately is one of the sample means. And perhaps that's the sample mean that we observed here in this case. What I do want you to notice again, though, is that the sample itself kind of mimics the shape of the parent. So when sample sizes are small, the parent will have a huge influence on what the samples themselves look like. And actually, if I run this sampling again many times, I'm now going to show you 100,000 sample means. So this blue distribution that you see here, that's the sampling distribution of sample means. You'll notice that there's that slight little tail on the right. So when the sample size is small and the parent population is not symmetric, then our sampling distribution is also not going to be symmetric. In fact, since in this case the parent population is skewed right, our sampling distribution of sample means will also be skewed right. All right, so that's how you would answer this question in part D. I'm not going to write that out, but of course you'd answer in context. And in this particular case, since the parent population is skewed right and the sample size is less than 30, then the sampling distribution of sample means would also be skewed right. I didn't mention any context there, so make sure you're citing context within your answers. Every context is king, ladies and gentlemen. Trust me on that one. All right, part E. Shift leader has suggested that she wants to use a random sample from Saturday night to plan orders for the next week. Describe a statistical problem with this decision. Also explain whether you think this decision will result in an under or overestimate of number of premium ingredients needed for the week. All right, so let's put it this way. This shift leader is only choosing Saturdays. Now, I think many of us, if not all of us, have been to restaurants on Saturdays versus restaurants on weekdays. And hopefully you've noticed that Saturdays are definitely bigger days for restaurants, okay? Restaurants are busier on the weekends. People don't have work the next day, you know, they want to go out and relax and have fun, blah, blah, blah. So by this shift leader only choosing Saturdays, or this particular Saturday, let's say, to plan orders for the next week, this shift leader is collecting a bias sample. Okay, so you want to use some sort of statistical keywords or vocabulary words anytime you answer a question. And in this case, the keyword is bias. So just a reminder, the way we define bias in our class is a systematic failure of a sample to represent the population. Well, why is this a systematic failure to represent the population? By only choosing a Saturday night, we're only looking at one in particular very busy night of the week. And so if we decide to order our ingredients based off of what we saw on a Saturday night, chances are we're probably going to overestimate, because I don't think Monday, Tuesday, Wednesday, I don't think those days are going to be as busy as Saturday, Friday, maybe even Sunday. Okay? So include the idea that this would be some sort of a bias sample because we are only we are not allowing our sample to be represented by other days of the week. Okay, and this would likely result in an over estimate of the order. All right, so the shift leader is not done working hard yet. She has calculated that Friday nights typically have 300 poke bowl orders. If each premium ingredient has a profit of $2, what is the expected profit? All right, so we have an expected value calculation. We now have a new random variable. We're talking about profit here, profit. So basically, I define this new random variable y to be 2 times x1 plus 2 times x2 plus ... plus 2 times x300. Each of these x's represents the number of ingredients that one of the randomly selected customers ordered, right? Again, I defined x way up here is the number of premium ingredients chosen by a customer, right? And so we're analyzing, whoop, giving away a lot of the answers. So we're analyzing 300 individual customers. And so customer one, let's say, orders X1 premium ingredients, and we will multiply those premium ingredients by 2 because each premium ingredient will result in a $2 profit. So we do that for each X outcome, and this is what we get for our random variable y. Now we want the expected value of y. So the expected value of y can be written as the expected value of 2 times x1 plus 2 times x2 plus ... plus 2 times x300. Okay. Now, if you remember the rules that we went over many times in class, I can factor out this constant from the expected value, and it really becomes 2 times the expected value of x1 plus x2 plus x3 ... plus x300. But of course, expected values, if I have an expected value of a sum of random variables, I can write that as a sum of expected values of that random variable. So this really, I skipped a step, so I'm gonna actually pause and fill in that step. All right, so I'm back. I filled in this row here. So basically, again, I factored out that constant, and I'm left with 2 times the expected value of x1 plus x2 plus ... plus x300. But this expected value of the sum of x's can be written as the sum of the expected value of x's. And so I'm left with 2 times the expected value of x1 plus the expected value of x2 plus ... plus the expected value of 300. And each of these is an x random variable. And so each of these has the same expected value. So really, I'm just summing up 300 of the same number. Or in other words, I can write that as 300 times the expected value of x. So I have 2 times the expected value, 2 times 300 times the expected value of x, which of course is 600 times the expected value of x. Here I go into detail about how to calculate the expected value, but remember we were already given that number. Mean and expected value is they're synonymous. So we end up with 600 times 0.97. So finally, the expected value of y is $582 of profit expected. Always include that context. All right, we're almost there, ladies and gentlemen. Describe the sampling distribution of the sample mean number of premium ingredients for this sample size of 100. Okay, so sorry, I skipped that. Finally, the shift leader takes a larger random sample. She takes each of the 50 weeks of the year and randomly selects 2 orders from each week. I don't know why there's only 50 weeks in a year, but I'm not arguing with it. It's fine. Now we describe the sampling distribution of sample mean number of premium ingredients for this sample of size 100. So now let's think about what we have. We have a random sample we have n greater than 30, and we also have independent selections because for each customer, we were told that these are their individual probabilities for number of premium ingredients. So that sort of implies independence. You could also think of it as that 100 is less than 10% of all customers over the entire year. All right, so the 10% condition is met. So since we have all these three conditions met, going in order, for shape, we have a random sample. Therefore, our sampling distribution of sample mean number of ingredients ordered will be nearly normal or approximately normal. Since we have a large enough, sorry, I'm going to pause for one moment. I'm tripping over my words. 1 second. Okay, I'm back. I just wanted to add some words. I just wanted to add some words to the screen so that you can see exactly what I'm referring to. So the fact is, we would need to check that the central limit theorem applies. And of course, with n greater than 30, the fact that we have a random sample and the fact that we have independent samples, or in other words, the 10% condition is met, that means the central limit theorem does apply. Now remember, and please, if you haven't done so, watch my video about the conditions for the sampling distributions of sample means, because I go over these concepts in a lot more detail. But basically, the n being greater than 30, that guarantees us that our sampling distribution will be approximately normal. With the random sample, that guarantees us that we have an unbiased estimator for the sample mean, which would be 0.97. So the sample mean, I'm sorry, an unbiased estimator for the distribution of sample means. And what that means is that our sampling distribution of sample means will be centered at the population mean. And again, and finally, sorry, the 10% condition guarantees us the spread of our sampling distribution. And specifically, it guarantees us that the standard error is equal to the population's standard deviation divided by square root of the sample size, which in this case is radical 100. Now, I'm not including context in my answer, but of course, when you describe this distribution, context is king. So make sure you're including context. There would not be any unusual features in this particular case. All right. I'm running out of steam here. Part H. I think since H and I are actually pretty similar, I'm going to just go over one of them in detail, and then I'll skim over the other one. Name this sampling method and describe a statistical advantage to using this method instead of simply taking a simple random sample. Now, they're referring to this method up here. Okay, and so this is a stratified sampling method. Why? Because she's breaking up the entire year up into 50 separate weeks. And I guess the idea is that each week is different than other weeks because some weeks are during holiday seasons where people are more likely to go out in higher numbers and also spend more money. Other weeks are during, maybe right after holiday season, let's say like at the beginning of January, people have been through many, a month worth of holidays. And so at that point, they're kind of not really willing to go out. They've spent a lot of money, so they want to start saving money. So, weeks after holidays might be very slow. So by stratifying the population into 50 different weeks, what we do is we guarantee that we're going to get, a little dose of week 1, a little dose of week 2, a little dose of week 3, blah, 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 all the way up through weeks 49 and 50. So we're going to get a little dose of each week, which, again, is a stratified sampling. And what this does is it reduces sampling variability. The statistical advantage to stratified sampling is always that it will reduce the sampling variability of whatever we're sampling, in this case of our sample mean. Why? Because it ensures that our sample will consist of busy weeks and non-busy weeks, right? So your answer has to include some keywords like stratified sampling, other keywords like reducing sampling variability of our sample mean. Also, explain why. Why would it do that? Don't just say, oh, it reduces the sampling variability. Make sure you're backing up your response with some reason why. All right, so that's part H. Part I is very similar. It's just that there is this understanding that Fridays, Saturdays, Sundays are different than the rest of the week, which makes sense. You know, weekends, people go out more. Describe and name the sampling method that would adjust for this observation. Explain the statistical advantage. Okay. This is another example of stratification. And so what you might do is you might take the entire week and stratify it by groups of days. Specifically, you might stratify your week into Mondays through Thursdays and then Fridays through Sundays. And you might want to go ahead and randomly select. So what are we trying to do? Select 100 people. You might want to randomly select. So this is what, 4 out of the 7 days. This is 3 out of the 7 days. So you take 4/7 of 100 people from here, and you take 3/7 of 100 people from here, so that you have a proportional representation of the non-busy days and the busy days in your sample. All right. And again, this will reduce sampling variability of our sample mean. Why? Because we are guaranteeing us a proportional representation of busy days and non-busy days. Again, please make sure to always answer in context. And that's that, ladies and gentlemen. So this is the video that goes over question 2 from mock exam 3. I had previously made a video for question 1. So if you need to go over that question, please check the channel. You'll find it. Hope this helps. Take care.